Hello, and welcome to today's session on the independent samples t-test. To put this into context, we'll be talking about t-tests in general today, and we'll also talk about different kinds of t-tests, at least some of the t-tests that we'll experience this semester. The first will be the easiest. It's a one-sample t-test, and then we'll expand upon that and talk about a two-sample t-test, assuming that we have an independent groups design. And then we'll talk about different kinds of independent samples t-tests. One will have a one-tail variety, or one will be of a one-tail variety, and one will be of a two-tail variety. And then we'll take a quick peek at what we might do in the classroom, in Excel, and also in SPSS. Before we get started though, as always, please make sure that you have the PowerPoint lecture notes printed and in front of you so that you can take notes along the way. Okay, let's begin by setting the stage a little bit about t-tests and harkening back to one of our earliest themes for the semester. During the first week of class, we talked about how we would return to the theme of correlational research versus differential research. Now, in recent videos, we've been talking about correlational research, and we've had some conversation, for example, about the Pearson R statistic. The Pearson R statistic is used if we have interval data or if we have ratio data, and this was developed by Carl Pearson. We also can use the R statistic, also known as the rho in the case of the Spearman's rho, if we have ordinal data on our two axes, and we can even look for correlations if we have categorical data. And what we had used for that particular analysis was the chi-square test of independence. So lots of different ways that we've had this semester to look at correlations or associations between variables, regardless of what kind of measurement scale we might have. What we'll do today is we'll start looking at differential research. We'll start looking at the case where we might have a control group and an experimental group, and how we might determine in a statistically satisfying way that those two groups are similar to each other or different from each other, and we'll be doing this in the context of a t-test. So, without further ado, let's first remind ourselves that when we evaluate the difference between any two means, we can't just look at the mean difference alone. We have to actually put the mean into context, and that's going to be an important and recurring theme for us today. We'll look at a difference in the context of some variability. And just to make another connection with some other work that we had earlier this semester, you'll remember that we had done descriptive statistics, where we typically look at some indication of central tendency, mode, median, or mean, and some indication of dispersion, like the standard deviation. We're going to start to put those descriptive statistics ideas together when we're talking about today's inferential statistic, which is the t-test. So for t-tests, the context is the variability, and the variability might be measured by something like the standard deviation or its near cousin, the variance. Let's begin though by first understanding this just by way of pictures. Okay, so here we have a picture and here we have a picture. There are going to be some important similarities and some important differences in these two graphs. On the left, we can see that we have the effectiveness of drug X, and we have two different kinds of treatments, drug X versus placebo. Over here we have the same layout, the effectiveness of drug X versus placebo, as our two different treatment groups, and we'll be looking at differences between means in these cases. The question is, which graph makes a more convincing case for drug X and why? Okay, so what we can say is that drug X has a mean of 8 here, and a mean of 3 for the placebo group, 5 for the placebo group here, 8 versus 5. Over here we have an 8 versus 5 difference. Hopefully, though, you've been able to see that the variability is very strong on the left side, and on the right-hand side, the variability is much reduced. The error bars are much shorter and hug the mean much more tightly in this case than in this case. Interestingly, the difference of 8 minus 5 here is a difference of 3, and 8 minus 5 here is a difference of 3 again. So we have identical differences between the drug and the placebo in the left graph and in the right graph, but we probably have a much more convincing case for drug X here than we do here. And that's because that difference of 3 is occurring within the context of a very small margin of error, as indicated by these error bars. By contrast, we have that same margin of 3, or difference of 3, but now the margin of error is quite a bit larger. So this would make for the more convincing case for drug X. Okay, so that brings us to today's mantra. T-tests compare means. Can we all say that together? Everybody? T-tests compare means. All right, that's going to be our mantra. We might add just a little bit to that, but it makes it a little bit less friendly to say, but it's t-tests compare means in the context of variability. Okay, So that's our little introduction to t-tests, and now we'll try to understand maybe the simplest variety of t-tests, which would be the one sample t-test, and after that we'll do a two sample t-test, and we'll talk a little bit about the different kinds of tails we can have in the two sample t-test after that. But first, the one sample t-test. So as I jokingly say, in ancient times, before the number 2 was invented, and before we could compare two means to each other, the ancient cavemen had used the one sample t-test. A one sample t-test is an evaluation of a single mean rather than two means. In most of the literature that you will read in psychological research, you'll see that we typically have a t-test comparing two means to each other. But you can have a one sample t-test, and we're going to compare one sample's mean to some sort of a test value, and you'll see that phrase in different kinds of statistical packages. You might see it in SPSS, for example, and that test value will have some kind of empirical interest, or be of empirical interest to you, or maybe theoretical interest to you. So here's an example. Consider the proportion of M&M colors in the population. There would be a test value for each color. So here we have the gloriously colored M&Ms, and I have taken this from Wikimedia Commons. It looks like a terrific picture. You can see all the different colors that we have here of the M&Ms, and we might have an idea about what proportions we should expect. For example, it might be the case that the manufacturer of M&Ms claims on their website that, for example, they have typically 24% blue M&Ms in a package, 14% brown, 16% green, 20% orange, 13% red, and 14% yellow. That might be something like the typical distributions of these different colors that we have. And maybe we're interested in trying to figure out whether it's the case that we have truth in advertising here. So what we might do is have the students in a class each have their own little packet of M&Ms. We have them open the packet, pour out the M&Ms, and count how many they have in each of these different color categories. And we might zoom in on one particular color just for simplicity. We might take a look at the allegedly 16% green M&Ms, and we might go to the first student and ask, what proportion or what percentage of green M&Ms did you have in your package? And that person would give us maybe one number. Then we go to the next person, what percentage of green M&Ms did you have in your package? And that number might be slightly different. And we go to the next person and the next around the room, and we can have now a whole list of numbers corresponding to the proportions of green M&Ms in each of those respective packages of M&Ms. And then we could take a mean from that, and we could take a standard deviation, and we would have some indication of this particular sample's distribution with respect to the green M&Ms and their frequency from a wider population. We could then compare that mean and that standard deviation to the alleged number of 16% and find out whether we're very close to that number or whether we're very, very different from that number. And we might use a one sample t-test to do that. The one sample that we would have would be obtained from all those different numbers, one from each student, and then we would compare that to the 16% and see how we do statistically. Let's take another example. Sometimes 2 or 3 examples will help us to understand this quite clearly. Assume that you're a therapist, and lots of our students do have clinical aspirations. So assume that you're a therapist who has received a sample of 20 patients with clinical depression. After 5 weeks of treatment, you might ask whether the mean of your sample is statistically indistinguishable from non-depressed patients who have means, for example, of 500 on a standard mood assessment test. So we're just making these numbers up for the moment, but you can imagine that if you're a clinical psychologist, there might be some readily available clinical data where you've got a distribution of non-depressed individuals, and their typical mood might be at something like 500. You're hoping that you can move your sample of 20 patients who are clinically depressed more into the normal range. And we can ask a question about what kinds of scores we have in your sample of 20 participants and how that compares to this mean value of 500 in the overall non-depressed population. Okay? So the null hypothesis might be something like this. Here's our HO, as you might recall from a prior video. And we have in the population as our opening phrase because we are looking just at a sample, but we're hoping to draw an inference about the population in general. So HO, in the population, the mean mood score of patients who have completed 5 weeks of my or your therapy is equal to that of non-depressed people. Okay? In this example, the test value would be equal to whatever the mean of the non-depressed population was, and we're saying, by way of example, that might be 500, so our test value here would be 500. Here's another example. We'll make this our third and final example for the one sample t-test. in the population, the mean age when first married is equal to 20. And we can take advantage of the general social survey, and we could look at something like 1,500 Americans who have been sampled by that survey, and we can ask how old they were when they were first married. And among those who are married and who have given us that information, we can compare that to some test value, which we're saying for the moment is 20. The test value, though, might come from any number of sources. It might be from some empirical research that you've done. It might be testing a prediction. Maybe there is a model of how marriage has changed over the years, and maybe there are some claims about mean ages when first married. So we might come up with a test value from any number of sources. In this particular case, we're saying that the test value is 20, and then we might take some steps in SPSS to see what this might be like if we were to compare the test value of 20 to an empirically observed mean. It might be something like 22.79 is what we would have in a sample from our general social survey. So we would compare the mean of 22.79 to our test value of 20. And we might see how those two compare. We can come up with a sig value that would tell us whether we should retain or reject the null hypothesis. So the sig value here indicates that we should in fact reject HO. And this brings us back to a simple decision rule that we have whenever we're engaged in hypothesis testing. If the sig value is less than 0.05, we reject. In fact, why don't we make that a mantra for today? Say it with me. If the sig value is less than 0.05, we reject. In this case, we're going to reject the null hypothesis, which was that there was no difference between the observed mean of 22.79 and the test mean. In this particular case, we assumed there was a test mean of 20. In a different study, there might have been a different test mean, but it looks like we are now significantly different from that, and our observed value of the alpha level, the sig value, is quite a bit less than 0.05. Right? Now let's say that we ran exactly the same sample with our mean of 22.79, but let's say, just hypothetically, we had a very different test value. Instead of it being 20 even, why don't we say it was 20.7? So now the question becomes, is 20.79 statistically different from 20.7? And the answer here is no. And the reason we come to that conclusion is the sig value, in this case, is up to 0.526, which is quite a bit higher than 0.05. You'll remember our rejection rule. When something is less than 0.05, or when the sig value, is less than 0.05, we reject the null hypothesis. Here the sig value is greater than or equal to 0.05, so we do not reject. You might say we retain, or perhaps we accept the null hypothesis. Okay, so the mean difference of 0.092 between this value and that value turns out to be statistically non-significant. Those two could be expected just by chance. That difference score can be expected just by chance, and this allows us to now retain the null hypothesis. Okay, typically we prefer to run two samples, one experimental group perhaps and one control group. However, that may not always be possible. We might have a sample, and we might have some indication of where that sample might be relative to some abstract standard, or some theoretically derived standard, or some earlier empirical investigation. And so we can compare that test value to our sample and see how we do using hypothesis testing, kind of like what we had done earlier for chi-square. Okay, so what we can do now is just take a little pause and have you stop the video and make a note of what to this point has been clear and what has been less clear. Okay, welcome back. And now we'll move on to the case of the independent samples t-test, where we're now going to be dealing with two different means that are empirically observed. We'll have a mean and a standard deviation for example, an experimental group, and we'll have one also for a control group. And we'll begin comparing those two to each other. Here's the formula. Looks a little bit intense, and we'll just unpack it one step at a time. So the formula for the independent samples t statistic will be x bar 1 minus x bar 2 over the numerator over this expression, which we will simply call the pooled variability. Okay? So we might ask, what does x bar represent again? Hopefully you'll recall that x bar is the mean of a sample. So this is our first sample. That might be the control group. Here's our second sample. That might be the experimental group. It is not always the case that 1 and 2 are control and experimental. They can be in any order. It doesn't matter which sequence we use. But we're looking for the difference between the means of these two groups. And then we're going to put that in the context of the variability. And this expression corresponds to the pooled variability. Okay, so now what we're going to do is zoom in on this denominator term. We're going to unpack it. Okay, and it looks a little bit nasty. I will not ask you to memorize this, but we're going to see how we might break it down and develop an intuition about how this fairly complicated looking expression actually corresponds to the pooled variability. So here's the denominator term in the independent samples t-test, and this is what we had seen in the previous slide. And if we want to do this computationally, we actually have to take the square root of this product. This item times that item. That product will be put underneath this radical sign so that we can take the square root of that product. Okay? Let's see if we can zoom into the first parenthetical phrase, and we'll ask you to harken back to something that we learned earlier. What does this S represent again? Hopefully you can take a moment to muse about that. You might remember that x bar corresponded to the mean, and little s corresponded to the standard deviation. If we take the standard deviation and we square it, we get to the variance. Hopefully you'll remember that the standard deviation is the square root of the variance, so we can take the standard deviation and square it, and we get back to the variance. And we're multiplying this by n1 minus 1. That's the number of people that we have in our first sample minus 1. And then we do something like that over here again, but now we do it for the second group. We'll take the variance of group 2, and the variance again is a standard deviation squared for group 2, and then we'll take the number of people that we have in group 2, that's n2, and we'll subtract 1 from that. Okay? Then we'll put all of that over the total number of degrees of freedom that we have here, and that's the number of people that we have in group 1 plus the number of people that we have in group 2 minus 2. Okay? And we're going to multiply all of that by 1 over n1 plus 1 over n2. So it looks like that's really quite a bit. What I hope will simplify this for you just a little bit, it's not a big simplification, is we can see that this harkens back to something that we learned earlier. This is essentially the sums of squares, and we'll see if we can make that obvious to you. In the next slide, you can see that we have roughly the same expression, but this has been simplified now to just the sums of squared for group 1 and the sums of squared for group 2. We'll flip back and forth between these two. This expression is a relatively complicated way of saying sums of squares, which is something that we had computed even during the first month of class. And we'll have a sums of squares for the first group, a sums of squares for the second group. We'll put that over the number of observations that we have. And you might remember that the sums of squares divided by the number of observations, or something like it, n minus 2 or n minus 1, would give us a variance. Okay? And then we'll multiply that by 1 over n1 and 1 over n2, and take the square root of all of that, and that will give us the pooled variance. What I'd like to do now is just see if I can unpack how we get from this figure to the sums of squares, just to do a little bit of review. I think that's important from time to time to review where these quantities are coming from. So I'm going to break out of this. We'll lift this up, and we'll just remind ourselves of some quantities that we've already seen. Remember that we have this quantity called the variance, and that we had computed the variance during the first week of class by computing the sums of squares for a particular set of scores, and dividing that by n minus 1 for the sample. And at this point in the semester, we're almost always dealing with samples rather than populations directly. Of course, we're trying to draw an inference about the population, but we're doing that by way of a sample. Okay, so we're going to do SS over n minus 1, and that will give us our variance. We could move those terms around just a little bit. So for example, I can multiply both sides of this equation by n minus 1. And if I did, that would make this n minus 1 go away, and I'd be left with the SS, or sums of squares, on the right side of the equation. And I'd have n minus 1 on the left times the variance. So n minus 1 times the variance gives us the sums of squares. And as I've alluded to already, we can just pull this down and have n minus 1 times the variance, which can be expressed as the standard deviation squared, or s squared. That will give us this SS. Okay? So n minus 1 times the variance, here expressed as standard deviation squared, will equal SS. Okay, let's bring that back now to the equations we saw a moment ago. And here we have our SS1 and our SS2. That's the sums of squares for the experimental group and for the control group. And back here, we have a more complicated version of that, n1 minus 1 times the standard deviation squared, which is going to be the variance. Same thing over here, n2 minus 1 standard deviation squared, and will give us the variance. So hopefully you can see how that all simplifies there. All right, that's about as complicated as we're going to get in this denominator, and if this is any consolation to you, I guarantee you that you will not have to memorize this formula. In class, we'll do some hands-on exercises where we'll begin to compute this, and we'll do it as a group. You'll be working on your Excel computer, but we'll be able to compute this denominator and put it underneath that relatively simple numerator, which was the mean of the first group minus the mean of the second group. That's the difference between the two groups put into some kind of context of variability, here the pooled variability. Okay. At some point, we're going to make a comparison between our observed value of the t-statistic and some critical value, just like we had done in the world of chi-square. And to obtain the critical value, we're going to need a criterion alpha level, which will, in our class, always be 0.05. And we'll also need to have some degrees of freedom. And the degrees of freedom formula for the independent samples t-test would be the total number of folks that we have in our study minus 2. Okay? And we will, in future sessions, begin to help you develop some intuitions about where this degrees of freedom formula comes from. But for right now, we're simply going to accept that degrees of freedom for this kind of statistic is n minus 2. Okay? All right, so now we're back to this diagram. We've seen this before, and hopefully we have an idea now, at least computationally, we have some idea about how the t-test is computed. And we've seen this before, the effectiveness of drug X compared to placebo. And the question is, which graph would be associated with a larger t-statistic? We'll let you muse about that for a moment. You can stop the video. Okay, welcome back. So if we look at the t-statistic, hopefully we can develop this intuition. We have the mean difference between mean 1 and mean 2, over some kind of variability. So if we drop back over here to the picture, we have a difference of 3, as we said earlier, and a difference of 3. So in each of these cases, the numerator is going to be 3. And then we divide the numerator by some indicator of variability. Here we have a relatively large amount of variance. Here we have a much smaller variance. So we have 3 over, if you will, a big number versus 3 over a small number. Okay? And 3 over a small number is going to generate a relatively large t-statistic. 3 over a much larger number, because we have larger variability here, will generate a much smaller t-statistic. So the t-value will be larger in this case than in this case. Hopefully that's clear to you. Okay, why don't we go ahead and talk a little bit about the assumptions that underlie the t-statistic. And this will be true for any t-statistic that you might compute as long as you have two different means, say independent samples t-test. And these should look familiar to you because these are the same assumptions that were underlying the Pearson statistic that we had computed earlier this semester. So here they are by way of review. The first assumption is that the distribution of scores should be bell-shaped. And we can have some tolerance there, but there will be indicators of how bell-shaped a distribution might be. And if we get a reasonably good match to this bell-shaped or Gaussian distribution, then we will have satisfied the first requirement. Okay, the second assumption is that the two populations from which the samples are selected must have at least approximately equal variances. Okay, so if the shape of the first one is about like this, the shape of the second one should be very similar. We wouldn't want to compare a distribution of scores that's very narrow to a distribution of scores that's very, very wide. And we'll have some quantities that we can get out of SPSS or other kinds of software packages that will tell us whether the variances of our two groups are sufficiently similar to each other to permit a t-test. And then finally, this third assumption is the assumption of independence. The value of any datum does not depend on that of any other datum. And we've talked about that previously in our conversation on the R statistic. Okay, how might we quantitatively assess the first assumption, the normalcy assumption? What we can do is get some indications out of SPSS that will tell us whether we have a strong skew, and we hope that we don't have any skews. That would be a really good way of determining whether we have at least met the first requirement for a normal distribution. We should have something that's symmetric. And we have other indicators of the extent to which a distribution actually matches a Gaussian curve. There are ways to test the equal variance assumption quantitatively. We'll learn about something called the Levene test. Okay? And then the independence assumption requires that we investigate how the data were obtained. This is not actually done through a statistical test, but we can just ask, is there something about the nature of the data collection process whereby a particular score depended on somebody else's score or some other score in the data set? And to the extent that we can say that every score did not depend on any other score, then we have satisfied the independence assumption. Okay, why don't we go ahead and have our conversation then about two tails or one. So here are some hypotheses for t-tests. Okay, we'll assume that we're dealing with a independent samples t-test, and we might say something like, in the population, the means for the control and experimental groups will be equal. This is often the case in a t-test null hypothesis. We speak of the equality of means. The alternate hypothesis, H1, would be in the population, the means for the control and experimental groups will not be equal. Okay, so just as we had done before, in the chi-square case, we can simply insert the not and change this to an H1, and we now have our alternate hypothesis, also called our research hypothesis. The alternate hypothesis is said to be two-tailed because it's not directional in this particular case. It does not state which of the two means will be larger. All we're saying here in the alternate hypothesis is that we would expect inequality. We didn't say that the experimental group would be larger or smaller in its dependent variable value than would the control group. Okay. So we might say then that we have this non-directional hypothesis, and this would be evaluated by a two-tailed t-test. Here's our Gaussian distribution. We can even think of this as a t-distribution, which tends to be Gaussian in shape, but it's a little bit different from a pure Gaussian. It's relatively bell-shaped though. And in our non-directional hypothesis, we can test for the most extreme 5%, 2.5% up here, and 2.5% down this way. And we can reject the null hypothesis whether we observed a t-statistic in either this critical region on the low end or this critical region on the high end. Okay? So what we'd be looking for then in order to reject the null hypothesis would be a relatively extreme score. Here's the 50th percentile, and we need to come up to something like the 97.5 percentile or higher to reject on the high end, or something back here toward the 2.5 percentile or lower to reject on the low end. Again, here's 2.5%, here's 2.5%, 2.5 plus 2.5 make 5, so these are the most extreme 5%, and in here we have the most typically occurring 95%. But what's interesting is, in order for us to reject the null hypothesis here, we have to be 47.5 centiles away from dead center, either on the high end or on the low end, and that's a relatively extreme score, and the more extreme the score gets, the less probable it is. There should be a probability axis over here, where lower values on that axis correspond to lower probabilities. Okay, here are some hypotheses for t-tests. In the population, the means for the control and experimental groups will be equal, just like before, but now watch what happens on the alternate hypothesis. In the population, the mean for the control group will be greater than the mean for the experimental group. And we're using here the word greater rather than the word not equal. So we're making, in this case, a directional prediction. The alternate hypothesis is said to be one-tailed here because it's directional. It tells us which mean will be larger than which. Okay, so now what happens is we're back to our t-distribution, which again is relatively Gaussian shaped, and we're still going to look at the 5 most extreme centiles. However, we're going to put all 5 of those up on one end, rather than having half of the 5% here and half of the 5% down here. Directional hypotheses are evaluated with a one-tailed test. So now what happens is we can reject the null hypothesis if we land in the rejection region, but critically, the rejection region is now only 45 centiles above this 50th percentile, not 47.5. So it's actually a less extreme score that we need in order to make this rejection. Okay, so reading that right off of here, because I realize it might not be easily seen on the video, we can only reject the null hypothesis when the observed statistic is in the predicted critical region all the way down here. And the observed t-value only needs to be at least 45 centiles away from the mean. So here's the 50th centile. We need to get up to 95, and 50 plus 45 would get us up to 95. But that 45th percentile as an increment is less extreme than it was back here, when we had to get all the way up to the 47.5 or 97.5 centile this way and 2.5 centile that way. Okay? All right. So when do we use the two-tailed test versus one-tail? And the answer almost always in science is it depends. If you want to make a directional prediction, use a one-tailed test, otherwise use a two-tailed test. Two-tails are often preferred because they are more conservative. And when we use the word conservative, we're not talking about political conservatism here. We're talking about inferential conservatism. We're cautious in our inference. We're inclined to want to avoid a type 1 error. And remember that because the two-tailed test puts us further out into the tails, That is to say, we have to go out to the 97.5 centile or the 2.5 centile. Those are more extreme scores, and it's less likely that you would catch one of those just by chance. Okay, so what we'll do now is let you jot down what kinds of things were particularly clear about this, what kinds of things were less clear, and then in class we'll do some exercises in Excel, and we'll also do some exercises in SPSS, and we'll see if we can get some hands-on practice with these concepts that are new to us today. I look forward to taking your questions in class. See you there.